Have you ever noticed something completely absurd about the universe? It's right in front of us, hiding in plain sight on your refrigerator. Take a tiny, cheap fridge magnet and hold it over a metal paperclip. Instantly, the paperclip leaps up, defying gravity. Think about what just happened. That tiny magnet effortlessly defeated the gravitational pull of the entire planet Earth. A planet weighing 6 ronograms. Earth is massive, pulling with all its might, yet a piece of metal the size of a coin wins the tug-of-war. How is this possible? In the realm of physics, this highlights a shocking fact. Gravity is unbelievably weak. It is the weakest of the 4 fundamental forces. Compared to electromagnetism, the force powering our magnet, gravity is weaker by a factor of 10 to the power of 36. That is a 1 followed by 36 zeros. To us, gravity feels strong because we are bound to this massive rock. But on a cosmic scale? Gravity is a pathetic, ghostly whisper. For decades, scientists have asked a mind-bending question. Is gravity truly this weak, or is it just diluted? What if gravity is the only force capable of escaping our universe? What if it is leaking into a parallel dimension? To understand this wild hypothesis, we need to meet the messenger of gravity. Or rather, the messenger we cannot seem to find. Everything in our universe is built on the standard model of particle physics. Think of it as the ultimate cosmic instruction manual. It describes all the fundamental building blocks and the tiny particles that carry forces. For example, electromagnetism is carried by photons, particles of light. The strong nuclear force is glued together by particles literally called gluons. But when scientists look for the particle that carries gravity, a theoretical particle named the graviton, the seat is completely empty. It is the biggest missing piece in modern physics. To find out why, we have to look closer, down to the quantum level. At CERN, the Large Hadron Collider accelerates protons to 99.9999991% the speed of light. When they smash together, they create a beautiful shower of exotic subatomic particles. We found the famous Higgs boson this way in 2012. But even in these extreme collisions, at record-breaking energies of 13.6 tera-electron-volts, the graviton remains completely invisible. Why can't we find it? Theoretical physicists suggest we might be looking at the fundamental building blocks all wrong. What if particles are not tiny, solid dots, but incredibly microscopic, vibrating loops of pure energy? Welcome to string theory. Just like different vibrations on a guitar string create different musical notes. Different vibrations of these microscopic strings create different fundamental particles, like electrons, quarks, and photons. But there is a catch. A massive one. The complex mathematics of string theory simply do not work in our standard 3D space. In a universe with only up-down, left-right, and forward-backward, the mathematical equations collapse into impossible anomalies and infinities. To make the math function beautifully, M-theory, the leading version of string theory, requires exactly 11 dimensions. Wait, 11? If there are extra spatial dimensions, where are they hiding? Why can't we walk into them right now? The theory suggests they are curled up and incredibly small. Billions of times smaller than a single proton. They are folded into complex, microscopic shapes called Calabi-Yau manifolds, invisibly woven into every point of the fabric of space. So, how does a universe with 11 dimensions solve the mystery of our missing gravity? Well, it introduces a concept. That feels like pure science fiction. What if our entire 3D universe is just a thin, flat membrane floating in a massive, higher-dimensional space? Imagine our entire observable universe, every star, galaxy, and black hole we have ever seen, is just a flat, three-dimensional membrane, or brane. We are essentially trapped, like tiny cosmic insects living out our entire existence on a single, glowing slice of bread. And just beyond our slice, separated by a mysterious higher-dimensional void called the bulk, there could be countless other parallel universes. In 1999, physicists Lisa Randall and Randall-Sundrum proposed a groundbreaking mathematical model based on string theory to explain this exact setup. But if other universes are floating right next to us, millimeters away in a higher dimension, why can't we see them? The answer lies in light itself. Remember our friend the photon? In string theory, particles like photons and electrons are open strings. Open strings have two distinct endpoints. And the fundamental rule of this cosmic physics is that these endpoints are securely tethered to our 3D membrane. No matter how hard they try, light and solid matter simply cannot leave our universe. They are physically stuck to our slice of bread. Because our eyes and telescopes rely entirely on light, we are completely blind to anything existing out there in the higher dimensional bulk. But the graviton? The mysterious missing messenger of gravity? It is built completely differently than the rest of the particle family. According to the mathematics of M-theory, a graviton is a closed string. It is a perfect, vibrating ring of pure energy. Because it has no endpoints to anchor it to our membrane, the graviton is not bound by our strict three-dimensional rules. Trillions of gravitons are completely free to float right off our slice of bread and drift away into the higher dimensional space. This leakage provides a mind-blowing, elegant answer to the tiny magnet and the giant Earth from our very first experiment. Gravity isn't intrinsically weak. We are simply experiencing the tiny, diluted fraction of gravity that hasn't yet leaked away into the multiverse. This elegant theory solves the gravity mystery perfectly. But in science, a beautiful mathematical idea is not enough. We need hard, physical proof. So, how do you prove that invisible particles are leaking into a completely invisible dimension? You look for what is missing. Welcome back to the Large Hadron Collider. Here, physicists rely on an unbreakable cosmic rule, the conservation of energy. Energy cannot simply disappear. If you push two particles together with a specific amount of energy, the resulting debris must contain that exact same total energy. Think of it like a cosmic accounting book. If 10 units of energy go in, exactly 10 units must come out. Always. But if the Brane Multiverse theory is correct, particle collisions at extreme speeds might occasionally create a graviton. Because the graviton is a closed string, it doesn't stay on our 3D membrane. It instantly floats away into the higher dimensional bulk. If that happens inside the LHC, the detectors will record an unbalanced equation. 10 units of energy went in, but only 9 came out. This phenomenon is known as missing transverse energy. And it is exactly what massive detectors like ATLAS and CMS are actively hunting for right now. The ATLAS detector alone weighs 7,000 tons and acts like a giant, three-dimensional digital camera taking 40 million pictures every single second. It scans the beautiful, chaotic aftermath of these proton interactions, desperately searching for a collision where a fraction of energy simply vanishes into thin air. To date, we have not found conclusive evidence of a graviton escaping. But the search is pushing the absolute limits of human technology. Which brings us to an even wilder thought. If we can theoretically detect gravity leaking out of our universe, could we intentionally force it to leak? Could we manipulate gravitons to send a message across the dimensional void? Could we build an interdimensional telegraph? To do that, we would need to generate our own massive, artificial gravitational waves. Unfortunately, a simple red button won't do anything. To send a message across dimensions, we need to create ripples in the fabric of spacetime itself. These ripples are called gravitational waves. Any object with mass creates them when it accelerates. Even you, waving your arms right now, are creating gravitational waves. But because gravity is so unbelievably weak, the waves you make are practically zero. To make a wave big enough to traverse the multiverse, we need to look at the most extreme events in the cosmos. In 2015, the LIGO Observatory detected gravitational waves for the very first time. The source? Two supermassive black holes, 1.3 billion light-years away, locked in a violent, high-speed spiral before merging into one. In a fraction of a second, an amount of mass equivalent to 3 of our suns was converted into pure, rippling gravitational energy. So, as a highly advanced civilization, here is our speculative blueprint. To build an interdimensional telegraph, we need a black hole engine. Imagine capturing two extremely dense objects, like neutron stars or black holes, and placing them inside a massive, artificially controlled orbit. By mechanically pushing them closer together or pulling them further apart, we can precisely control the frequency of the gravitational waves they emit. And in the world of communication, if you can control a frequency, you can encode data. We are no longer just making noise, we are writing code. A short, high-frequency burst could represent a dot. A long, low-frequency rumble could represent a dash. The ultimate cosmic Morse code. Using our black hole engine, we could continuously blast an artificial gravitational pattern out into the extra dimensions. A simple message. Because these waves are made of gravitons, those closed strings that aren't glued to our universe, the message completely ignores our 3D boundaries. It travels relentlessly through the pitch-black, higher-dimensional void of the bulk, a beacon of intelligence screaming into the dark. Until, eventually, the ripples wash against the shores of another membrane. Another parallel universe. But who is there to listen? When our artificial gravitational waves finally wash over the adjacent cosmic membrane, they would cause microscopic, rhythmic ripples in their spacetime. Perhaps a highly advanced civilization there has built their own massive detectors, watching their screens in awe as a cosmic hello arrives. But communication is a two-way street. If we can send messages, shouldn't we be looking for invisible signals coming from them? Look around our own universe. Is there any evidence of invisible, unexplained gravity pulling on our stars and galaxies right now? The answer is a resounding yes. Astronomers call it dark matter. It is the invisible scaffolding holding our entire universe together. Observations show that normal matter, everything we can see, touch, and interact with, makes up only 5% of the universe. Meanwhile, dark matter makes up a staggering 27%. There is 5 times more invisible stuff out there than visible stuff. We know it exists because of its massive gravitational pull. But it is completely invisible to light. Photons just pass right through it. For decades, we have searched for a new, exotic particle to explain this invisible mass, but we have found absolutely nothing. What if we are looking in the wrong place? What if dark matter isn't a mysterious particle inside our universe at all? Here is the mind-bending hypothesis. What if dark matter is just the gravitational shadow of ordinary matter sitting in a parallel universe? Imagine a massive, glowing galaxy of stars existing on a parallel membrane, hovering just a fraction of a millimeter away from our own slice of space. Because light cannot cross the bulk, we cannot see their stars. But remember, gravitons are closed strings. Gravity can leak. The gravity from their parallel galaxy leaks across the void and pulls on the space in our universe. An invisible, mysterious tug. To us, it looks exactly like dark matter. But in reality, it might just be the cosmic reflection of our multidimensional neighbors. If our universe and a parallel universe are truly floating side by side, sharing a gravitational pull, it raises a terrifying, ultimate question. Gravity is an attractive force. Over billions of years, this invisible tug would inevitably draw the two cosmic membranes closer and closer together. What happens when they finally touch? To answer that, we have to look back to the very beginning of everything. We know that our universe is expanding. If we rewind the clock 13.8 billion years, everything shrinks down to a single point. The Standard Model tells us the universe began as an infinitely hot, dense singularity that suddenly expanded. The Big Bang. But where did that singularity come from? String theory and the Brane Multiverse offer a completely different, mind-blowing origin story. In 2001, physicists Paul Steinhardt and Neil Turok proposed the Ekpyrotic Universe model. It suggests that before the Big Bang, our universe was completely empty. It was a cold, dark, perfectly flat membrane floating in the bulk. And right next to it was another, equally cold parallel membrane. Drawn together by mutual gravitational leakage, they accelerated across the microscopic gap. And then, they collided. The Big Bang wasn't an explosion from nothing. It was the spectacular, brilliant collision of two parallel universes. The immense kinetic energy of the crash was instantly converted into a blazing hot soup of plasma, radiation, and fundamental particles. Like two cymbals crashing together, the branes bounced off each other and began to drift apart again, expanding and cooling as they went. Over 13.8 billion years, our bruised and battered universe cooled down. The plasma clumped into stars, galaxies, and eventually, us. But the heat of that initial interdimensional crash never truly vanished. It just cooled down to 2.7 Kelvin above absolute zero. We can still see it today. It is the cosmic microwave background. The ultimate, absolute proof that our universe was born in a firestorm. If our Big Bang was just the result of two brains interacting, a terrifying but beautiful thought emerges. What about the other slices of bread? In an endless bulk space containing infinite parallel membranes, gentle cosmic interactions and brilliant bursts of energy must be happening all the time. To put this into perspective, our own observable universe is absolutely staggering. It spans 93 billion light-years across. It contains roughly 200 billion trillion individual stars. That is a 2 followed by 23 zeros. A number beyond human comprehension. Faced with the concept of a multiverse, it is incredibly easy to feel entirely insignificant. A microscopic speck on a single slice of bread. But remember this. The atoms in your body were forged in the hearts of dying stars, born from that very first cosmic interaction. You are not just a spectator in the multiverse. You are the universe itself, given consciousness, trying to understand its own magnificent existence. So, what about that message we sent? The artificial gravitational waves carrying our hello across the dark bulk? Perhaps, billions of years from now, it will wash over another membrane. And perhaps, an intelligence there will build their own black hole engine. And they will send a reply. A new set of gravitons, traveling backward through the dimensional darkness, carrying a simple, profound truth. A signal that our distant descendants, watching their ultra-advanced gravitational wave detectors, will finally receive and decode. A message proving that in this terrifyingly vast, dark, and infinitely layered multiverse, we are not entirely alone. String theory and the Brane Multiverse remain unproven hypotheses. But they offer a beautiful vision of a universe deeply connected to others. So the next time you drop a magnet on your fridge, take a moment to wonder. Where exactly is that missing gravity going? Thanks for exploring the multiverse with us. If you survived this mind-bending journey, hit subscribe, and we will see you in the next dimension.